Hola amigos, welcome and thank you for dialing in on the first day of our TezIndia Blockchain Bootcamp. I'm Siddharth and I'm your host for this bootcamp organized by Tezos India in collaboration with Code8. So first, let's go over event itinerary. On the very first day, we will have an introduction to blockchain technology, starting off with what is blockchain, and then moving on to the prerequisites of blockchain development and consensus algorithm. After all the theory, we will learn about smart contract and its applications, and ending with the introduction to Tezos platform. After that, on the fourth and fifth day, we will be working on projects. You will also get mentorship from our side on this project. Today, we will start off with what is blockchain and its prerequisites. Just a little housekeeping before we kick off. If you have any question during the presentation, please type your query in the YouTube chat box. These questions will be brought up during the presentation, and also we will be taking questions at the end. Now, I would like to request everyone to turn on their interaction on the chat box to make the session more interactive. Now, without any further ado, we will turn the time over to Ojasvi Rastogi. He is a BTech undergraduate working on business application on the Tezos blockchain, having mentored and contributed to open source events like MLHP Fellowship, GSSOC workshops, and being a tech enthusiast with expansive knowledge on today's topic of discussion. I can assure you that you will find the session very interesting. Ojasvi, now you can take your phone.
Hi. Uh, Thanks for this warm welcome. Welcome guys to a 5-day journey of this bootcamp. I saw your all responses in the registration form. So much excitement. That would be great to use it here. So I'll share my screen. I have a slide ready, and we'll learn through that slide. It includes many of the concepts of blockchain. How does it look? How does it work? And some underlying concepts of cryptography. So today, today we are mainly going to cover that. It's mostly theoretical, but not boring. I'll just share my screen and we can get started. And of course, in between, if you guys have any question, you can always share that in the chat and I'll answer them as soon as I can. So can anyone confirm that? Is it visible?
Yeah, or just for your screen is visible. I guess there is a little problem in your video feed. So just check your video if it is a problem.
Okay, so let me just a second. No, not visible. Just no. Yeah, there we go. Hi. It should be visible, right?
Yeah, obviously.
Okay, so we are good to go. So let's begin with the journey of blockchain. We are going to cover everything from very starting. So if you are a beginner, don't worry, we got you covered. And before just starting with the blockchain properties of blockchain, I'll just give you a very brief introduction to it. And what is it actually? So I'm expecting that all of you know about general web development that we all do in Web 2.0. We have some front end which is made using some languages, HTML, CSS, vanilla JavaScript, maybe some framework, React, Angular. And then we have backend. Backend can be in Node.js, it can be in Django. There are so many different frameworks where we can make backend. And to store data, we have some database. So MongoDB is a very popular example of it. We also store on Postgres, MySQL, and there are many old databases also. But in general, this is a basic structure of a very basic structure of a Web2 website. Front end connected to back end connected to database. So in Web 3.0, we are modifying some of the stuff. We are merging backend and database into one. So you don't have to make query to some external database. I mean, you can, of course, depending on what application you're making. But generally, if it's a blockchain, it's a backend and a database mixed into one thing. Plus, there are some other differences which we are going to cover in the further slides, right? So first of all, the first property of blockchain is that it's immutable. When we say something is immutable, that basically means that it's very difficult to change it. Like if you have a database, if you have a blockchain, and you started working with it, the blockchain is up and running. In between of the running process of the application, you cannot change it. You cannot change the way it's working. For example, you have a backend, maybe of Node.js, it's connected to a CI/CD pipeline. You push your code to some version control system, maybe GitHub, and it gets automatically updated. Your code is automatically updated on the backend, right? So you can update it on real time whenever you want. We can't do that with blockchains, and it's not a bad thing. It's a good thing actually. So when you have something which can be up and running and it cannot be changed, it gives us many of the applications that we can build something on top of it, and we will see those further applications. But this is one of its property. So blockchain looks like this. It's a chain of blocks. That's why it's called a blockchain. And whenever you try to modify something in between of it, it gets invalid. And when it gets invalid, then you can't use it. So uh, there are some other replacements for it, and it gets replaced by the correct blockchain. We will study all of that further, but this is just the first property, that we cannot mutate the blockchain, the code of the blockchain. The next property is it's decentralized. Now, this is a very good property. So in traditional system, in Web 2.0, you have that backend, that a database, and it's mostly hosted somewhere. So you have a backend, it's mostly running on some Linux operating system, Linux distro, on some virtual private server, also called as VPS. Now it can be Heroku, it can be AWS, Google Cloud, Microsoft Azure. There are so many services where you can just host your backend there. Similarly, we can do the same thing with databases. The problem with that is it's just hosted on one thing. So, for example, if it's hosted on Google Cloud and the Google Cloud goes down, all of the servers that are hosted on Google Cloud also goes down. And we have seen this in the past. I mean, probably 1 or 2 months earlier, we saw this, that Google basically went down and all of the backend services that are up and running on Google Cloud also went down. So the whole world kind of panicked that, oh my God, my website is not. So that's a very basic caveat of it, that when you have something hosted on one thing, it's bound to go down someday or the other. But when things get decentralized, um, the service is not hosted at one place, it's hosted on multiple places. So you can imagine it like your backend is hosted on AWS. The same backend is also hosted on Google Cloud, Microsoft Azure, Heroku, maybe on your computer, maybe on your friend's computer. The same backend is hosted everywhere, and all of them are connected to each other. So this is how we can maintain decentralization. Decentralization means which is not centralized. When things are centralized, it's only um, hosted at one thing. But if it's decentralized, it's hosted on multiple things. So blockchain also works this way. It's decentralized. Okay. The next property, it's a distributed ledger. Now, what do we mean that by that? So distributed is another name of decentralization, which means that the work that the blockchain is doing is distributed, and it's distributed across multiple peers. You can also call them as nodes. So it's distributed among all of them. And whenever you want to do something with it, whenever you want to do something with a blockchain, you simply add that change into a block, you put that change into a block, and then add that block to the blockchain, to append that block to the blockchain. So it's easy to explain it in this example image. You have these multiple nodes, and all of these are having these this blockchain hosted onto them. So whenever you want to um, modify the data into that blockchain, because data is also into the blockchain, it's a mixture of database and backend. So it also holds some data. And when you need to change that data, you can just append that new data to the previous blockchain. You cannot change the previous blocks. You can only append the new blocks. And that resembles the procedure of a ledger. And that is why we call it a distributed ledger. Do we have a question? No. Okay. Cool. You can always come to learn Tezos, right? Next property is it's more secure than anything else. I mean seriously. And you have a like you can even imagine Google Cloud. Google Cloud is way more secure. It's way more secure. There are thousands of cybersecurity experts working on that somehow they can manage to not let it go down. But it does. I mean, everyone does the mistake. And similarly, we have seen with Facebook also. Recently, Facebook's domain name was up on some website for sale, and some guy bought it, I think. I mean, these kind of things are way very evident then that things are never much secure, never enough secure. But when we come to blockchain, it's way secure than anything centralized. When we come to blockchain, if you try to attack a server, for example, we see in this diagram, we got these multiple nodes hosting some blockchain, and let's say someone attacked the blockchain on this server. Well, there's no problem. They attacked the server, they changed some node in between, but still other connected nodes to it will observe that change. And then they can simply disconnect this node from everyone else. So everyone will basically disconnect from this node, and the rest of the nodes can simply keep working. They'll continue to work like nothing happened. So mostly the power hackers use to attack is never greater than the power combined with the nodes. Okay, so that's mostly the case, and this is how this whole delicate system cannot be broken. You cannot attack in between some single node and then expect the whole blockchain to collapse, because it cannot. It's all connected together. If something goes wrong, it just gets disconnected. Mostly disconnecting the node is not the best option. Sometimes we see that this node also wants to get better. So they basically replace their own blockchain with the connected nodes. And those are the concepts which we can learn ahead. The next property is transparency. Blockchains are always transparent. which is a very good property. For example, if we see the diagram here, the same data and the backend, which means all the algorithms which your application are using, and the data which your application is holding, that whole thing, that algorithms and the data, all of that is hosted across multiple nodes, right? So there is no centralized server, and it's not like the data is in just one server and it cannot go out. With blockchains, it's completely opposite. You have this node, and that all of the data inside that node is always visible. So if you have these multiple nodes, you can basically connect to any of the nodes and then fetch the data of the blockchain. You can even host your own node, and then you can download the whole blockchain into your node onto your laptop or computer, and then read all of the data that's inside that blockchain. So this gives us the freedom to completely make it transparent, which is a good thing. I mean, imagine Facebook's algorithm and data being open, but the private data is encrypted, but the the thing which should not be encrypted, which is not private, it's all public. So that way, you can never accuse them of stealing data. Right? Similarly, we can have Twitter. Twitter's, like the recent controversy is that the algorithm of Twitter. So the algorithm of Twitter should be public. So imagine if Twitter was built on blockchain, then the whole algorithm, the code of the Twitter, the inside core code of the Twitter is always open. It will be open source. So anyone can look at it. Anyone can look at the data that they are holding. So this transparency um, kind of takes the power from the centralized um, organizations to public. And when things get decentralized, the power is always distributed amongst all of the participants, including us. And that makes us that makes it a better system than that we currently have. So next property is consensus protocol. So blockchains, uh, we already observed that blockchains are not a single thing. They are they are basically multiple nodes and having the same blockchain. Now, there are many problems which arise when you have this kind of distributed system, because I mean, let's imagine this case only. We are adding a new block into this blockchain, but then we can also add some other block on some other blockchain or of some other node, and then both of the blocks will be mm, not same, they will be different. So how will they uh, kind of decide that which block should be put first and which block should be put second? Because after all, somehow they have to figure out that all of the blockchains are same. But when we keep adding the blocks, things get messy and uh, they can confuse. So for that, the blockchain is always having some consensus protocol, which is basically, in simple words, is an algorithm which all of the nodes uses, so that things never get stuck. They always know what to do if they ever face any dilemma that um, which blocks to put first, or um, which block to put first or which block to put second, or which block to mark as invalid and then discard. All of those rules and regulations that people follow in their codes is written into the code, and that complete procedure, you can also call it as protocol, you can also call it as algorithm, that's called a consensus algorithm. So blockchains always have that, and that is a very major factor that how a blockchain performs, how efficient it is, and what are the advantages of it. So There are many consensus protocols for many blockchains. Bitcoin was the first blockchain with proof of work. Then we got proof of stake. We got proof of history, of future. There are so many protocols, but some of the most popular ones are proof of work and proof of stake. The next property is trustless. So this is a very cool property. You have this blockchain hosted on multiple nodes, and whenever you make a transaction on the blockchain, a transaction is a change in the data of the blockchain. We can simply understand it like that. So when we do a transaction on the blockchain, I'll show it using this diagram. So this guy is adding a new block. Now, sometimes you can put false information in the block and then add it into the blockchain. Now, obviously, this is not correct. You cannot add. You should not add the false information into the block, but you always can do, because I mean things are at least in this side, things are in your control. It's your own copy of the blockchain, so you can add a false information in, and then tell all of the other nodes that, all right, I just added some new block. You guys can also add it too. But the way blockchain is made using many cryptographic algorithms, it's made in such a way that you can always verify that if the data inside that block is correct or not, if it's valid or not. We'll learn some of the very basic stuff in the further slides, that how does it work. But it's always possible that you can basically instantaneously determine that if a block is valid or not. And so you never need to trust anyone. You just need to trust the mathematics behind that algorithm, which decides if the block is valid or not. You always need to trust that those algorithms, those mathematics. You never need to trust the people who are hosting the blog. You can always say that, okay, this guy may tell the truth, may tell the lies, but at the end, if you follow the consensus protocol and if you do the exact things that are told in the consensus protocol, you can always use those mathematics to verify that if the value inside the block is correct or not, if the data that has been put inside the block is correct or not. So this system creates a very trustless environment, because you never need to create any trust. For example, here you see Alice, who is having her own distributed ledger. She adds something into it. Maybe that's a simple transaction that she's probably sending some coins to Bob. And then all of the people who are participating in the blockchain can always verify that using the mathematics, that it's the Alice only who is trying to send her own tokens. It's not anyone else who is trying to um, mimic the look of Alice, and it's not anyone else basically. So it's very difficult to do any kind of man in the middle attacks or anything, because you basically have these cryptographic functions which can very easily let us know that if a transaction is valid or not. We never have to trust anyone else who is participating in the blockchain. Like in Bitcoin also, we have a node, we have some other nodes, but you never need to know that who else is hosting the node, because the procedure automatically works without knowing that. So it's very good to be it's very easy to be anonymous in a blockchain system. You just need to create a new wallet and no one knows you. That's how it can manage that. So these are the properties of it. um, it- this gives us a pretty good idea that when do we need to use a blockchain. It's not like every project needs a blockchain. That's not the case, right? Sometimes you need it, sometimes you don't. And how do we decide that? You can decide using this. So if everyone needs transparency, if you want that the data should be public and there should be not much hidden in the data, you can use blockchain. If you want it to be immutable, if you want to store something which should never be erased from existence, then you should use a blockchain. If you want security, if you want that almost no one in the world can ever put this system down, you definitely need a blockchain. Bitcoin never went down because, I mean, so many hackers have tried to do something so that Bitcoin goes down, but it will never. I mean, we have already seen that if things are decentralized, it's very difficult. And again, if you need decentralization, if you want to distribute the power amongst all of the participants, but just not use a kind of a server and client system where there's a single server, a centralized server, and all of the clients are connected, and the server have all the power. If you don't want that, if you want a complete um, decentralized system where all the participants have equal power, then you should use a blockchain. And if you want it to be irreversible, which means anything which have been added into a blockchain should not be taken back. So it's always, that means it's always irreversible. For example, if you send some bitcoins to some other guy, you cannot reverse that. You cannot undo that. So that is also a case when you need a blockchain. So these are the cases, and these cases are required in many places. This is just a very small list. When you want to transfer some money. I mean, this is one of the first example that was used with Bitcoin. And then we got voting mechanism. Voting mechanism is a very good application. I mean, if you have some decentralized way of voting, then everyone will get equal power. They can um, they can vote, and then whatever data is saved after the voting will never be more modified. I mean, no one can modify that. It's immutable, right? And everything is also transparent. So at the end, when you get to count the number of votes, that value is never um, tampered, right? So things are transparent, which means it's perfect for voting. So similarly, we got so many applications. Each day we see some new application with blockchain, and things are developing very fast. So voting mechanism, supply chain monitoring, NFT marketplaces. We got a lot of NFT marketplaces. We can create personal identities. I mean, we can have Aadhaar card on blockchain. So you will have your own personal identity, which cannot be changed. And you can always look at who generated that identity. The whole blockchain is public. So you can go back in the blocks and look at that time that who created this NFT, who created this identity. And that way you can always verify that who was the actual person who audited it. And that's how you can um, identify any kind of identity card or certificate or anything. Lending insurance, we got a ton of projects on that. Data storage, 5 point. Gaming, we have so many gaming projects that are being built on many different blockchains. And yeah, it can be anywhere where we need to eliminate corruption. Corruption happens when things are not transparent and when power is only at the one single side. That is a very kind invitation to corruption. So a very pure way to remove is that simply use blockchain. So everything will get transparent and then the data will be distributed. sorry, power will be distributed. So these were all the properties of blockchain in general. Many other blockchains have many their own specialized properties. Like Tezos also have their own specialized properties. We can have a look at that later. But um, these were the properties that we generally see. So if you guys have any question till now, we can take that. We can definitely take that. And um, you guys might have some problem in the later parts if you are unclear with these stuff. So make sure to drop your queries if you are doubtful in any of the case.
Okay, Rajeshri, we have two questions till now. So
Cool.
just answer them. So Crypto Talk Bangla asked that I don't know coding of any kind. Should I continue with the sessions? Is it like I will be asked to do coding later in the boot camp that I will not be able to do?
It's up to you. If you want to code along with me, you can. I mean, obviously it's not compulsory, but uh, you will definitely um, get more experience if you try to code it yourself. And if you don't have much prior knowledge of it, you can still get very basic understanding of what blockchain is and some of the topics that are required to understand blockchains. But and also you can still get to know how projects basically work with coding in general. So if you want that kind of learning, you can definitely stay.
Okay, Bree asked that what is proof of work and what is proof of stake?
It's proof of stake, not state. It's a STAKE. Okay. And these are the consensus algorithms which we generally see with the blockchains. Blockchains always have some consensus algorithm. And like if I give you an example, it can be it's like it's an algorithm. Um, like do you want to know the complete algorithm, or do you want to know about the algorithm, that what it actually does, or do you want to know that the complete procedure that happens within that algorithm? I'm quite confused what I was asking.
I guess continue with just about that.
Okay, so it's basically an algorithm which tells you if let's say you are a part of the blockchain, you are a node, okay, and you get confused at some point that which block to add and which block to reject. Now, there are other nodes also who are waiting for you to decide, and in between of that, some other node uh, interrupts you, and they also tell you that they also have their own node, their own block ready to be appended into the blockchain. And now you guys are all confused because there are, I mean, thousands of nodes for a blockchain. So you can always have that tendency to confuse that in what order should you put the nodes, and what are the valid nodes, what are the invalid nodes, which, sorry, nodes, not nodes, what are the valid blocks, what are the invalid blocks, which block will basically give you more value by adding, and um, if it's valid or not. So all of these kinds of questions can be covered if you follow some rules, right? Some procedure. And if all of the nodes follow these procedures, the blockchain will keep on working forever. So this procedure is the consensus algorithm. This procedure is called a consensus algorithm. Consensus basically means coming to a conclusion where you got multiple entities trying to argue that what should we do finally. They basically needs to come to a conclusion, and that is called a consensus. So consensus algorithm is some algorithm, some procedure which every nodes follow with their own individual speed, and that procedure is made in such a way that the blockchain will continue to work if everyone will follow that procedure correctly. So that is consensus protocol. Now there are many types of protocols, and the two main examples, the two major examples that we generally see with multiple blockchains are proof of work consensus protocol and proof of stake consensus protocol. So I hope that clears it up.
Okay,
Any other question?
let's just end up with the last question. We will take the rest of the questions in the end. So Rushil Kothari asked that how is a chain managed in a blockchain once it becomes very large? Would it consume a lot of space to store all the data of the blocks? Is it efficiency tested in such a case?
That's a very good question, and I hear that question a lot. So, um, I mean, that's definitely one thing which is very important to focus, because whenever you develop a blockchain, I gave you an example of Google Cloud and Facebook, which have so big databases, but generally we don't need that big of a database. Generally, the things that are needed, just the security part, transparency part, they are a very small numbers, so they generally don't get too big. The second thing is there are um, many procedures which happens within the consensus protocol, which helps you to kind of optimize the storage. Like obviously we um, convert the data into bytecodes and then save into the blockchain, but still the nodes are all are of different types. There are, like, I have seen two types of nodes. One is called a normal node, and then other one is an archive node. So not all the nodes are archive nodes, but the job of the archive nodes is that they have to store all of the data. So that data is very large. They basically store TBs and TBs and TBs of data, which they are a subset of the they are a subset of all the nodes. And then we see some of the snapshot nodes, which basically takes the hash of the complete data and then just continue to add the blocks from there. So that basically takes a snapshot. It's a very easy to understand name. That's a snapshot of the complete data, and they take that data into their node and then continue the blockchains from there. So that way, because mostly you don't need much of the information from way past in the history, so they keep on taking the snapshots periodically and then uh, set their nodes accordingly to that. So yeah, that should answer your question, that archive nodes are the type of nodes which saves everything, and then we got the snapshot nodes too. So this is how they kind of optimize the storage, and not everything is stored on the blockchain. Very less things are stored, just the things that are required.
So just do you want to take some more questions or we should take them at the end?
Um, we can take one or two more questions if you like.
So Pri asks that how do we meet the growing market of blockchain if we can't change the code?
Can you repeat please?
Pri is asking that how do we meet the growing market of blockchain if we can't change the code?
Okay, we can't change the code. Okay. Yeah, good. So the code that we are talking about are basically called smart contracts. Smart contracts. That's the name of the thing that we are referring to as code. And smart contracts are made in such a hierarchical way that you never need to modify the complete system of smart contract. For example, if you are building a project, you will have multiple smart contracts for each of the small responsibility. So, for example, in an NFT marketplace, you have a smart contract to store data. Then you have a smart contract to store NFTs. Then you have a smart contract to have a marketplace for that. Then you have a smart contract for auctions that you can bid and um, basically play auctions with NFTs. So you have separate smart contracts, and we definitely need to update the code. And when you need to update, you can basically replace that smart contract with your newly hosted smart contract, and then connect those smart contract to the remaining of the previously connected smart contracts. So this is how we kind of update the um, the the application. And sometimes this is also not enough. So you basically create a new version of the complete application. So the storage is still there; it's never erased, but you create a complete set of new smart contracts and then link it to the previous storage. So that's how we update the code. And if in case you got some human error into that code, which can be a vulnerability, then it can definitely be exploited. We have seen these cases in the past that such vulnerabilities are always exploited. So it's always recommended to get your smart contract audited by multiple people so that it should not contain these kinds of vulnerabilities.
Okay, so we have another question from Cryptotalk Bangla. Cryptotalk Bangla asks that most of the things are automated. Then how can one put malicious data? Like we don't approve transactions manually, the system runs and it happens automatically.
I mean, it's hard to hear your voice. Can you type the question?
Am I audible now?
Yeah, yeah.
Okay, so Cryptotalk Bangla asks that most of the things are automated. Then how can one put malicious data? Like we don't approve the transactions manually. The system runs and it happens automatically.
Hmm. So things are automated, definitely. Things are very automated, but it's automated for normal people. When you are a hacker, you try to mimic the computers as much as possible, and you kind of just change the inner things which which will not be automated, which will be manual, and then send malicious transactions into the blockchain. So for example, let's say whenever you kind of send a transaction to the blockchain, it's called an operation, and the process is called injection. So you inject an operation into the blockchain. Now within this process, the injection is we basically inject a hashed bytecode of the operation, and you can always recreate that operation yourself using the same algorithms which automated procedures have, and you can recreate your own malicious bytecode and then inject it into the blockchain. So you are basically recreating the whole automated procedure and then doing it manually, and that's how you can enter the malicious data.
Okay, so we have a last question from Ujjwal Kumar Gupta. So Ujjwal Kumar Gupta asked that what's the recommended system configuration for a node?
I mean, it's a very uh, general question. I mean, there are many blockchains, and some of the blockchains also supports multiple types of nodes. So are you talking about the configuration of archive or main node that we talk about? Archive and the snapshot. I think that's what you are talking. So
You can explain that. You can explain
hmm,
that.
hmm. So the recommended way is always an archive one, but it also depends on how much resources do you have. I mean, I don't think you would want to host an archive node of thousands of TB. We don't have that much space. So uh, we always have this we always need to make this decision that what are your trade-offs, because of course hosting an archive node will also give you more incentive. Basically, when you host a node, you uh, get some incentive for that in terms of cryptocurrency. So Bitcoin mining is an example of that, that you host a node of Bitcoin, you mine Bitcoin, and in return you get some of the parts of the Bitcoin into a wallet. So that's how you earn Bitcoins using mining. Now, if you're hosting archive nodes, you'll get more incentive, but then you also need to give more data storage. So it's a trade-off, and it depends how much you can afford and how much you want to earn. So there's no recommended way. There's always your own calculation for it, that how much resources you need to allocate into.
So we can continue with the session. There are no more questions for now. Let us take the questions at the end.
Yeah. So we just a second, let me take some water. So we have looked at all of the properties of the blockchains. Now let's move to the prerequisites to get to learn the consensus protocol. If you need to understand the consensus protocol and many of the small concepts of blockchain development, you should have some pretty good knowledge of some of the cryptography, and that comes as a prerequisite to everything. So we are going to cover that today. So the first prerequisite is hashing. Now, hashing is, I mean, I hope some of the people knows that, but hashing is kind of a function. It's a process to convert one type of value to another type of value using cryptography. What is cryptography? Cryptography is kind of a study of mathematics which you can apply on some values and then use the outcomes for some application. I mean, that's a very basic understanding of what cryptography is. So hashing is one of the application, and in this we have some algorithm, some function, mathematical function, and you pass a value into that function, and you get something in return. So uh, for for in this case, it's basically like your fingerprint. Let's say there's a human. Now, a human have a complete a very large data set all around their body, right? I mean, there are so many cells and so many data. So if you need to identify a human, you cannot go and compare each of the cell of the human and then conclude that, okay, this is the guy that we needed. So a very efficient way to do that is using the fingerprints. You basically take a fingerprint of some person, and then whenever you need to identify them, you can just compare the fingerprints. And digitally, that's way more easier. So a fingerprint is a very similar example to hashing. In hashing also, we have large parts of data, and if we need to compare that, if the parts of data that we had earlier and the parts of data that we have currently, if they are same or not, you can basically hash both of them. You'll get a value which will be very unique and distinct, just like a fingerprint, and then just compare that small value. So it's it's too it becomes very easy and efficient when you're using hashing. So hashing have its own properties. Like when you are using a hash function, that function is kind of a formula, and it always gives you a fixed size output. So I mean, there are examples of it, like SHA-256 is a very standard um, hashing algorithm that we see in many places, and they have a very fixed size output, up to 256 bits. So this is how this is one of the properties of hashing functions, and they are always expected to be unique. So whenever you give some input, I mean, there are properties of hashing functions. Let's move to that one. These are the properties. First of all, it's a one-way trip. So like if you have a person, you can get the fingerprint of that person, the fingerprint from that person, but you cannot go back. You cannot reverse, and let's say you got a fingerprint, you cannot recreate a person from a fingerprint. So in terms of hashing, this is how it works. You have tons of files, you hash them, and you get a very small value. But what you can't do is you have a small value and then recreate the whole set of files. That's never possible. The functions are created in this way that this is never possible. The second thing is it's deterministic. So by deterministic, we basically means that if we have some set of files and we hashed it and we got a value out of it, then some point in the future, at some point in the future, you take the same set of files in the same orientation and then hash them again. Then you'll get the same value that you had in the previous try. So the same input always gives the same output. That's the small explanation. The third point is it computes the result very fast. So it's like a linear time algorithm. You take some input, you hash it, and that hashing process is very fast. It takes like no time to generate a hash, a small set of alphanumeric characters, and then again you get a very small set of alphanumeric characters. Then it's very easy to compare them and save them. Then yeah, one of the best properties of it is it shows the avalanche effect. Now, what is the avalanche effect? The avalanche effect is that, let's say you have a very large um, large set of files. Let's say it let's say you have a text file of 10,000 characters. Now those 10,000 characters will have some hash value, but then if you just change the last letter of it, let's say the last letter was C and you change it to D, just the last part of the whole input data is changed, that will result in the catastrophic change in this hash value. The hash value will completely change. It's not like you change the last part of the input, so you'll also change the last part of the output. That never happens. If you change just small part of the input, you'll get a completely different output. So very small change will lead to a very large change in the output. That's the avalanche effect, and a good hash function always follow that. And then finally we have a very good property that it can withstand collisions. So when you have collision, now what is collision? Let's say you have some files and you hash them and you got a value. Now you at some point of time you again take some other set of files which are different from the previous one. You hash them with the same algorithm, but still you get the same output. So in the beginning, as an input, we got two different inputs, but the output is same. This case is called a collision. This is called a collision in a hash function. Now, a good hash function have very less collisions, very negligible amount of collisions mm, in in the lifetime of universe. I mean, very negligible amount of collisions. So, I mean, if you take SHE 256 for example, then the probability of having a collision within that algorithm is 1 divided by 2 to the power 256, and that's way more universally big a number, which is expected to have a happen level. So that is a good hash function, and I've explained all of that. We got one way hash function, deterministic hash functions, which always gives you a input for the same output for the same input. The next thing in the summary is their speed. Hash functions are very fast, so I mean they mostly for a small amount of input data, you can take it as a constant time thing. Then you got the avalanche effect. If you just change just a minor thing in your document, the complete value of the hash function is changed. That is called the avalanche effect. And this makes it very difficult to predict. I mean, let's say let's suppose if in case the last value of output is only changed and all of the output is always same, then you re kind of almost go the reverse trip. In that case, you will have this almost 95% of the hash same, so you can predict the input that was given into the function. That is possible if it doesn't show the avalanche effect. But if it shows the avalanche effect, you cannot predict the previous input that was given into the hash function, which makes it very secure. And hash functions should withstand collision. So this is an example of a bad hash function. You got a dog and you hashed it, you got a hash value. You got another dog, you hashed it and you got the same value. Now, whatever algorithm you use to hash it is not much good because you saw collision. So good for hash functions always try to avoid these. And we also have some tool for that. So I can show you these properties. So this is some online tool where we can hash any of the input data, and we will get the so whatever I type here, just random letters, and we got some hash. Now, no matter how big I keep adding it, no matter how big, the size of the hash function is always same. It's always 64 characters. Plus, if I change just the last thing, currently the last, I don't know if you can clearly see it. Maybe now you can. So just the last letter of this whole big data is E. But if I just erase it, see what happens at the hash function. It's completely changed. That was the avalanche effect. And let's say if I take this whole data and try to remember the first or last few characters of this hash function, I take it back and then I input them again. Most probably you are looking at the same hash value. That shows us the deterministic property of a hash function. So this was a small demo of hash function. I hope it resolves most of your queries if there were. Now, where do we see it? We see it in Bitcoin. Bitcoin uses SHA-256 hash functions, and we see hash functions in digital signatures. Digital signatures are kind of a similar way to mimic real life signatures. You basically can authorize yourself on different places using your own generated digital signature, and it's very heavily used in proof of work consensus that we will study. And chain is made using hash. Yeah. So what does that mean by that? So a blockchain is a chain of multiple blocks connected in a linear fashion. But the only thing that connects them is hashing. It's not like a linked list where you connect them using address. On blockchains, it's connected using hashing. So, I mean, in simple words, what happens is you have a block, you hash that block. So a block size is very big, but you hash it, you take a very small value, and then put that value in the next block. And that's it. You keep doing that. This creates the connection because the hash is stored in the next block, so you always have this kind of a connection. And this type of connection is very useful that we will get to know in the further sessions, that how does it make sense to connect them like that. The next thing is encryption. Okay, encryption, I mean, that's a pretty what to say that common thing that we see in a lot of places. So encryption is kind of a cipher thing. You have some input and you apply some mathematical formulas to that input to get an output. Now, this output is never readable. It's uh, it appears a complete gibberish to human brain. It's a complete gibberish. You can never understand what's written in an encrypted value. But then you applies the reverse algorithms onto that encrypted data, and then you can get the same data back which was earlier encrypted, and that is plain and that is human readable. So this is how encryption works. So you have some plain text, you scramble it, you, maybe some using some specified algorithms. There are multiple algorithms for that, but you basically scramble that, and that creates a very gibberish kind of cipher text, which can be then reversed using this reversed algorithm. Now, this is not a one-way trip, it's a two-way trip. You can convert a plain text to an encrypted text, and then as a reverse procedure, you can take that encrypted text and then decrypt it to get back your plain text. This is how basic encryption works. And mostly when you are encrypting a plain text, you do it using some key. Now, key is sort of like a password. You took a plain text, you entered that password, and that password just that password is put into that algorithm along with your text, and that is how you get your um, encrypted text. And then you do the same thing. You take that encrypted text, you put it into the decryption algorithm, enter the same password, and then get back the plain text. Now, if the password is different, then you will never get back the plain text. You'll get back something else, some other kind of gibberish, because it messed up the whole algorithm. It was never encrypted using that key which you entered. It was encrypted with the original key. So whatever I just explained you to here is a type of encryption which is called a symmetric encryption. This is how it looks like. The property of symmetric encryption is that keys are same. The encrypting key and the decrypting key are always the same. If you change any one of the key, you will not be able to decrypt it successfully, and you will never get the plain text that you were expecting. So yeah, it uses the same secret key. And let's say you want to send this message to your friend or someone. So the system works like this, that you and your friend will have the same keys. You both know each other, and you have the same key. So whenever you encrypt it using your key, your friend knows that, okay, I got this message from this guy, so I'll decrypt it using this key, and that will give you the plain text. I can show you a very basic demonstration of that. AES, Advanced Encryption Standard, is a very standardized symmetric algorithm. So I can show you how it usually works. Let's say I have my friend somewhere across the world who is watching this stream, let's say. So I'll enter a message here, let's say hello, and I'll select the mode for it. Let's say we both have decided to use ECB, and then we enter some key size here. So let's say the key is let's say the key is 1 2 3 4 5 6 7 8, and then we encrypt it. Yeah, just a second. Change that. Can 16 bits key size of 16. I'll probably miss something. 16 bits. 16 bits to secret key should be 16 for it should be 16. That's too much. 0 1 2 3 4 5 6 7 8 9 8 should be enough. Not getting the output for some reason. If it doesn't work here, I'll try to orally recreate the procedure.
So there is a question regarding this. Rushan Kothari is asking whether it is a public or public and private key.
No. So the concept of public and private key comes into the picture when we talk about asymmetric encryption. That's another type of encryption which we will study just after this one. But in the symmetric encryption algorithms, you only have one type of key, which is generally called a secret key. So public and private keys are different things, which I'll explain in the next slide, where we'll talk about the asymmetric encryption. But for some reason, this doesn't seem to work. Stop working. That's good. Yeah, we can decrypt, but it's not encrypted. So that's a very good time to hit the sites. Okay, so I'll just already recreate the procedure. You have some plain text which I wanted to send my friend. We encrypt that using some secret key. This is the secret key that we agreed on, and then we encrypt it. And here we get some kind of a gibberish, very random thing which cannot be understood by anyone. And then I send this thing through the public to my friend. Now everyone in the subset of public can kind of read this data, but they cannot understand it because it's humanly gibberish. But then my friend takes this data and then put this data into the decryption algorithm, and they already know the secret key, so they enter the same secret key and then decrypt it. So that will give me the same plain text that I entered earlier. That is how the whole symmetric encryption works, which we mostly don't see in blockchain. In blockchain, we see asymmetric encryption. Let's come to that. Here it is. This is asymmetric encryption, and it's very cool. So a very easy way to differentiate between both types of algorithm is that in symmetric encryption we have a same secret key, but then in asymmetric encryption we have two different types of keys, two different keys. One is called a public key, and the second one is called a private key. So you have a plain text. You can encrypt that text using any one of the keys. Shown in this example, we got public key encrypting the plain text. Then you get a very cipher gibberish. And then we need to decrypt that document using the other key that was not used in the procedure of encryption. So in this case, public key was used to encrypt. That means we need to use a secret, which is also called the private key, to decrypt the ciphertext. That is how you successfully decrypt it. You cannot use the same key to encrypt and decrypt. And these keys are generated using some algorithm, which is connected to the algorithm of encryption and decryption also. So yeah, and one more thing is generally generally the way we use this algorithm is that a private key is always kept with you. Like for example, in my case, I will always carry my private key safe and secure and never reveal that private key to anyone. And the public key is known to everyone else. So I can always send this public key to anyone, any anonymous person, any stranger or anyone. But I will never reveal the private key. This is how we this is the standard way of using this algorithm. And why is it useful? We'll see that in the examples. Just making sure we didn't miss anything. Yes, no to everyone. Yeah. So the reason for that is, let's say you want to let's say I want to send a message to my friend. So how will I do that so that I never reveal the actual message to the complete world, just to my person? So I'll take my message and I'll encrypt that using my friend's public key, and and then I'll send the encrypted message to my friend. Now my friend will decrypt that message using his own private key. He has it, so he can definitely use that. And then the private key will decrypt the message successfully because the message was encrypted using the public key. So this is how you can maintain the security of the data. I mean, no one else in the world have that private key, which means no one else in the world can decrypt that data. Only my friend have that private key, so only my friend can decrypt it. And I always wanted always wanted to save that message for my friend only. So that's why I encrypted with his public key only. The second way we can use the same encryption is is kind of is for kind of signatures. I mean, it's not a proper way of using signatures, but it's the same thing. But in this case, we encrypt the data using private key. Now, why do we do that? Let's say I want to broadcast a message, but that message is so anonymous, maybe in the blockchain space only. So I want to broadcast a message to the whole world, and I want some kind of method so that the world can easily understand that okay, this is me only that who is sending the message. This is not someone else who is trying to mimic me. Now, a very easy way to do that is I will just encrypt my message using my private key and then broadcast that message to the world. Now the whole world have my public key. So they will take my public key, decrypt it, and then successfully read the message. And they can easily verify that I was the only one who created that message because it's successfully decrypted using the public key, using my public key, which means it was encrypted using my private key, which is only with me. So that's how we can mathematically prove that it was only me that initiated that message. That's how you can um, prove the um, authenticity of any kind of message, or maybe media, or maybe document. You just basically encrypt it using your private key and ask others to decrypt it using your public key. So you can use it in both of the ways depending on what you want from your message. So digital signature is the thing that I just explained to you. Now, a very small differentiation in that is you basically hash it um, before encrypting it. So that kinds of create a whole create a kind of a standardized procedure which other people can use just to verify the signatures. Why do we need this? We need it because in previous case I encrypted the whole message. Sometimes people who don't have my public key also want to view the message. Well, what do we do in that case? For that, we kind of have a procedure where a key is the signature is in separate place and the document is intact. So you send both of them. You send the document also, and then you send the signature also attached to it. And that signature is produced from the hash of the document. So that is how if someone have the public key, they can verify the signature. And if they don't want to verify the signature, they just want to read the information, they can always do that because the document was never encrypted. It's always intact. So digital signature is also one of the things which uses asymmetric encryption behind it along with hashing so that they can prove the authenticity of any kind of data. So that's uh, that's almost like the that's almost needed. That's almost everything that's needed from the cryptographic viewpoint that you need to learn blockchain development. And if it's between you ever get stuck, you can always learn the specific topic because the only prerequisites are included here. So you never get stuck with that. So that's the end of the cryptographic viewpoint, prerequisites of it. From the next session, we will learn about the much weighted consensus protocols, and that will be way more interesting than today's lecture because it will help you to visualize many of the things. It will help you to visualize how blockchain works, how is it so secure, how is it so unhackable, unattackable, that sort of stuff. So that's it for today. If you guys have any questions, keep dropping them in.
So there are some questions, so I will just dictate them to you. So Satish Kumar Reddy asks, what happens if wrong secret key is provided?
You can always give the wrong secret key to your friends to mess with them. But I mean, if you give the wrong secret key, the message will not be decrypted successfully. So the decryption will basically fail. It will not fail, but it will decrypt it incorrectly because the secret key was not same. So that's what it will happen.
Umang Prasad asks that can the public and the private key be same?
No. Mostly, if you are using some standardized algorithms like RSA or something, RSA or elliptic curve digital signature algorithms or Edward digital signature algorithms. Like there are many types of digital standardized digital signature algorithms, and if they are adopted by the world, they will never produce the same public key and the private key. They are always much different.
Okay, related to this, can you give us can you give them an example like how the both the keys are different?
Okay, so you want the example. Let me just let's see if we can have that. Yeah, hopefully the generation is working. Yeah, this is here is the example. I used the RSA algorithm. I selected the key size of 1024 bits and then generated the keys. Now the keys, public key and private keys are always generated in pairs. You cannot do like let's just create one type of key, private key, and let's just ignore the public key. That never happens. Keys, if you're dealing with asymmetric encryption algorithms, keys will always be paired. So here also I just generated two keys, and this is how a private key looks like, and this is how this is how public key looks like, and this is the private key. Key itself looks like a gibberish, but it works like it works very robust. Let's see if it's working here. Let's type hello. Maybe. Let's see if it's working. I'll type my public key here. using simple RSA. The key type is public key, and we encrypt it. Yeah, we got the encrypted output. Now take this output. I give it to my friend, and now let's start supposing that I'm a friend. So I'll take this value, get the private key this time, not the public key, because public key was used for encryption. For decryption, we will use private key, and using the same algorithm, I decrypt it, and I got hello. If in case the private key was different, it will show me decryption error. So hopefully this example clears all of it.
Okay, we have the next question for Martin Parmar. Martin Parmar asks, in case of blockchain, which keys are used at sender side and the receiver side?
Okay. In case of blockchain, we always want transparency. We don't want that you send some encrypted message, encrypted data into the blockchain, and no one can understand it. You never want that. You want that you send the data, everyone can read it, and everyone can verify that it's only generated by you. In that case, you always encrypt the data using your private keys. This is also called signing. Whenever you are dealing with transaction, you always, before sending the transaction, you sign it using your private key. Whatever wallet you are using, it will always ask you to sign it. You just click a button, it signs it, and then send it to the uh, blockchain. And signing happens using a private key.
So the next question is from Ujjwal Kumar Gupta. He have a question related to the Tezos platform. So Ujjwal Kumar asks, do we need to join the public Tezos blockchain to use Tezos in any application, or each application can have private blockchain?
You can create your own private blockchain if you want, but it won't give you the sense of decentralization and transparency. For example, it depends on your use case, like what are you expecting from your application. If you are creating, let's say, a kind of supply chain consortium, then you will create your own private chain across multiple companies, and only those companies will have the access to that chain. But if you are creating some DeFi protocol or some NFT marketplace, then you need to deploy your application on the public blockchain.
So that's all questions we have received till now. If anyone have any other question, please drop them in the chat box. We'll wait for a while. I guess that's all question for today. Ujjwal, is there anything you want to cover up before wrapping up and moving to the quiz?
I just wanted to appreciate that I got really good questions. I mean, these are the type of question which uh, I really like to discuss about. So thanks for that.
Okay, so now as we are moving to the end of this session, now we will have a quiz regarding today's session. So I will just share my screen and we'll move towards the quiz board. So just you can stop sharing your screen so I can share.
Sure.
Okay, so there you go. I will drop the quiz link in the chat box. Also, you can go to this link and directly join from there. I would request everyone to join the quiz link fast so that we can move on with the quiz. Everyone join the quiz fast so that we can proceed. I guess we have 15 participants. So I will just start with the quiz. All the best, everyone. More participants are joining. We'll wait for 5 minutes more and then we will start the quiz. Is anyone else is joining or shall we start? So let us just start the quiz. All the best, everyone. I will share the leaderboard after the end of the quiz. So I guess we are done with the quiz. I will just start sharing after some time. After some time, I will be sharing the leaderboard. Still, still five players haven't finished the quiz. We'll just wait for them. Then we'll start sharing the leaderboard. So I guess I should start sharing the screen out with the board. First of all, a round clap of applause to Siddharth Das Gupta for acing the leaderboard with a score of 15,450 points, followed by Ujjwal with a five streak of and a score of 12,380 points, and then Himanshu Kushwaha with a score of 12,210 points. Thank you all of you for participating in the quiz. Still four players are remaining. We'll just wait for them, and the complete leaderboard will be shared with you after a while. Ujasvi, is there anything that you want to cover up before wrapping up today's session?
Okay. I mean, good work, guys, with the quiz. That's very appreciable.
Still some players are working with the quiz. I guess 22 out of 26 players are done. So let's just end the quiz right here. I guess we are taking too much time. I will just end the game right here. So thank you everyone for joining in on the first day. We will again see you tomorrow with more interesting stuff. Tomorrow is going to be one of the best days because tomorrow we will be learning about the census algorithm. I hope you all join tomorrow. All will join tomorrow. Thank you and have a great day ahead.